Template classes are commonly used for operating on containers. Here I have a working copy of template class.cpp from Chapter 8 of the exercise files. This is a simple LIFO stack, last in, first out. There's a more complete version in the standard template library. I've created this simple version so we can see how it works. So if we scroll down here, you see that I have a simple exception class. I'm using that for error reporting. And then here, starting on line 18, is my template class. I call it stack. And the important thing to notice about this is that there's nothing in this that really cares about what type is being used with this stack. And so when we come down here to the code that implements the stack itself, you see that I use comparison operators and I return a stack pointer and a few things like that. It's really a very simple class. And when I actually use it, I implement it like this. I say stack and I give the type that the stack is using inside these angle braces. And I initialize it with a stack size of 5. And we see our constructor here, which is right here. It uses that size, which is an integer, to initialize an array of whatever the type is that's being used in the template. And then coming back down here, I'm using cout here because I'm already using the STL, so I don't mind using cout. And so I look at the size of the stack, I look at the top of the stack, which returns an index into the stack, and the stack is numbered 0 through whatever the size of the stack is. So this is a stack of 5, so the top of the stack will be 4. And then I use a range-based for loop to push 5 values onto the stack. And then I look at the top after the pushes, so that should say 4. It should also say full. It checks this is full method, which returns a Boolean value if the top of the stack is greater than or equal to the size minus 1. And then it pops the values off the stack and it looks at those values while it's popping them out. And I do the same thing with strings. And so this is exactly the same code with strings. Now, when I build and run, you see that our stack size is 5. The top is -1 because it's 0 based. I return a -1 if the stack is empty. After the pushes, the top of the stack is 4. That's correct. And it is full. And then I pop the values 5, 4, 3, 2, 1. And then I do the same thing with strings. Stack size 5, top -1, top after the pushes is 4. It's full, and here's our values, 5, 4, 3, 2, 1. And you can see that this same code is working with both strings and integers, 2 entirely different types. One of them is a fundamental type, the integers, and the other is a class type out of the standard template library, the string library. So this is possible because of templates. I write this code once, and I'm able to use it with different types. You'll also notice that I'm using exceptions for my error reporting. That just makes the error reporting really simple. I don't have to have a lot of logic around it. And so if I try to push too many values onto the stack, for example, and I build and run, you see that my first time through, it says stack error, stack full. And that error message is right there, stack full, if I'm trying to push past it already being full. And I just check that is full member function. So you see, this makes the code very simple. There's really nothing very complicated about this, and yet it's able to handle stacks with different types of values in the stack. So template classes are especially useful for manipulating containers of items where the logic of the manipulation is independent of the type. That's why the C++ standard containers are written using templates.